I'm Joe Carroll. This is a brief panel, 45 minutes to an hour. There are three of us here. It's on construction. I'm actually 72 years old today, and I've been involved in the space business for now exactly half my life. I started in '36. And what I'm finding is that when I put together slides, I usually end up wanting the title to have a question mark at the end. I didn't do this when I first started in aerospace because I thought I knew something. Now I'm trying to hand off to other people the questions that still bother me 36 years later, okay? So construction in space, question mark, is intentional, okay? So I have Al Globus and Rob Hoyt, who will also be talking about this, but I'm going to start with two more slides to underscore the question of what the questions might be. Okay, so one of the questions is, will you build a house in space or will you dig it? Okay, and this is a serious question to my mind. And partly, if you're building it in low Earth orbit or in free space, you will be building it. If you do it anywhere else, or if you hollow out an asteroid or recycle it, it's going to be digging it. Let me ask, how many of you have ever been to the underground gardens in Fresno? Okay, one person plus me. I've been there twice. But, okay. It may be the closest thing that you will ever see in your life to what might be used in space, okay? And it was dug by one person over some 47 years and is now available for tour most of the year, not middle of the winter, midweek. But the underground gardens, you can find it, www underground gardens. It's definitely worth seeing, okay, and thinking about. And these four pictures at the bottom are all from it, okay? It's a nondescript site. You look at it and there are just trees popping out of the ground, okay? It gets interesting when you get under. So this is something you ought to be thinking about. Now, more generally, what you need and what you have and your creativity is going to drive everything that you do. In Siberia, they found that when they wanted to make hydropower dams to run the gold and diamond mining, it took a year and a half to get cement. And so they found that they could make something ersatz cement using permafrost, using ice instead of cement. Now, doing that with water dams sounds challenging, but they figured out a way to do it. Okay, now with global warming, the so-called permanent frost may not be very permanent, but this is the kind of creativity that you only deal with when you have a need and have idiosyncratic limitations on what you have available. And it's your creativity that determines what you do, okay? That's all I have to say on construction other than the big question mark, okay? So let me, Rob, you ready to?
Sure.
Rob Hoyt is a competitor of mine. My company is Tether Applications, and Rob's is Tethers Unlimited. I'll let him finish the description of his activities related to this because he's actually doing some work, funded work, more related to construction than I have.
Yeah,
okay,
all right.
Great.
Okay, sorry, thanks for your patience. So yeah, I'm Rob Hoyt from Tethers Unlimited. We're a small business up in Bothell, Washington. And overall, what we're trying to do is help create a robust and sustainable economy in space to help support humanity's expansion out to become a truly spacefaring society. But since I tragically am not an internet billionaire, we're starting small and building up these capabilities incrementally. So I'd like to just show you a few slides, talk about a few of the projects we're working on. But overall, what we're trying to do is address the full supply chain for in-space manufacturing and in-space services so that we can stand up a viable economy in space. So our overall grandmaster scheme for conquering the solar system is, as I said, we started out small, developed a handful of high-performance components for very small satellites, line of software-defined radios we now have over half a dozen of those flying, supporting a number of government small sat programs. We also developed a thruster called Hydros, which uses water as propellant, and in part because we believe that water can serve as a key resource for creating an in-space economy. And then now we're starting to integrate some of those components together to create our own small sat platforms where we can provide hosted payload services and then build upon those small sat platforms, assembling a number of them together to build persistent space platforms to provide hosted payload services and serve as a business park in space, supporting in-space manufacture, in-space assembly, in-space refueling services, and other kinds of in-space services to help a in-space economy grow. So the small sat components are mostly out of R&D at this stage, and our focus with them is on ramping up production capability, ramping up our quality assurance so that we can support the big primes who are building government constellations of small sats. But the in-space manufacturing, in-space assembly technologies are in the R&D and starting to move into the flight demonstration stage. And I'll tell you about a few of those fairly quickly. One of the missions or one of the services that we are working towards is a microsat class robotic servicing system that we call Leo Knight. The system will use a compact robotic arm that we've developed called the Kraken. It was originally funded by, its development was originally funded by NRL almost 10 years ago, and now we're building one to go up inside the space station to enable teleoperation of experiments on the station, and we're working with the Air Force Research Lab to mature it for use on the exterior of small satellites. And the reason we're focusing on a small sat platform for this is the existing robotic servicing vehicles like Restore-L and RSGS that the government is currently investing in are very large, high-cost spacecraft, hundreds of millions of dollars, and the economics of that isn't really terribly favorable for actually doing in-space assembly of microsat class components. So we're focusing on Leo Knight, this small sat class system that we can build for somewhere between $50 to $100 million and perform in-space assembly missions, assembling modular space platforms, in-space refueling, helping to sustain low-altitude flying satellites, and other in-space manufacturing and in-space services. A little bit more technical detail on the Leo Knight. Although the system as a whole is relatively immature, it's built around components that have high maturity, particularly our radios. As I said, we have a number of those flying. Our robotic arms, which currently are at roughly TRL 5, so we've got a working prototype in our lab, and over the next 18 months we'll be putting together the first qualification unit and then flight units. And then of course the Hydros thruster, which as I said uses water as propellant, so we can go and tank up at a water fueling depot and deliver water propellant to small satellites that hopefully use our thruster or other water-based thrusters, such as those developed by Deep Space Industries and Momentus. And, another aspect of that is we've been developing basically a tool set to facilitate capture and servicing of satellites on orbit. It's called Dactylus. Dactylus is essentially an end effector or tool that goes at the end of the Kraken arm, and there's an associated servicing port that will get integrated onto satellites before they are launched. And that tool set will facilitate capture of a satellite so that it can be refueled or upgraded or otherwise serviced. And then, then we've been working under a number of small business contracts from the Air Force and NASA to develop a set of tools to enable in-space services, in-space manufacturing, servicing. Of course, the Kraken arm, we've got a video of that working on our Facebook page if you want to check that out. It's designed to fold up and stow into a very compact volume so that it can fit into a very small satellite, but then two of them will unfold to give you basically the same reach and dexterity as a set of human arms. Of course, the Dactylus connector and the Axon connector is another connector technology to facilitate in-space assembly of modular space systems. And then for the past 6 or 7 years, we've been developing a technology called Trusselator to enable in-space manufacture of high-performance structures to support things like large antennas, long baseline, interferometers, those sorts of things. And we're currently underway on a flight mission development. There'll be a press release on that coming out in the next few weeks. But we, knock on wood, we should be flying a key element of the Trusselator and demonstrating in-space manufacture of a very large space structure on orbit on the Restore-L mission in 2021. So I'll stop there and turn it on over. Mm-hmm.
I'm going to just get from here.
Okay, now we have Al Globus, and you can describe your relevant background in construction in space.
Yes, I've built millions of tons of hardware in space. Sorry, I don't have any slides. I just found out I was on this panel a few minutes ago. But and I haven't built a lot of stuff like Tethers Unlimited has. It's very impressive and really good stuff. And I think I see a way for it to be integral to some of the stuff I talk about. My main interest is building space settlements, and in particular building the first space settlement. But for the purpose of this discussion, I would like to open that up a little bit and say to build the first N space settlements where N is some largish number, like 10 or 20 or 30 or something like that. And that changes the problem quite a bit. The problem of constructing these things. Now, the basic idea is that you put your space settlement in equatorial low Earth orbit, which I talked about last session, and now you conceptually you put it there. So now here's the problem of actually building it and then building the next 10 or 15 or something like that. The way to go about this is to build something very small that's similar, that can maybe make some money, and as I described, the idea is to build space hotels. You can build a space hotel with a single launch. And you can make some money. Whether you can make a profit or not, I really don't know. I don't know whether that's going to happen, but I know you can make some money, because there have been 9 tourists that have flown to the International Space Station. Actually, 8 tourists, one of them flew twice. So there's 9 missions, and they paid a lot of money, probably somewhere between $20 and $50 million apiece. So there's actually some revenue that has been demonstrated. Now, let's suppose that things go well, and you build your hotel and it makes money, or at least doesn't lose too much money, and so you'll build another one. You'll probably want to build it a little bigger and a little better. And you build another one after that, and it's a little bigger and better. And so on and so forth, and you get to the size of a decent space settlement. Minimum size was probably 112 meter diameter. That's 4 RPM to get 1 G. And then you build a couple of hotels at that size, and you probably spin those hotels. So even though one of the main things you want to get out of going in the hotel experience is floating in gravity, you probably want a little bit of G on the outer rim. So when you put your fork down, it stays there. okay? And much more important, you don't have to learn how to use a zero-G toilet. Okay, now I have not any experience with zero-G toilets personally, but I have talked to people who have, and the short story is it's hard, you will screw up, and it will be gross. Okay, and if you're spending $10 million to take your dream trip to space, that might not be the sort of experience you're going to be willing to put up with for very many years. So in any case, you probably want a little bit of spin. That also means that your staff will be in an environment where they have a little bit of G and they can probably last longer. And you can still, your customers can still go to the axis of rotation and get free fall. Okay, so you can still get what you want, you just don't have it quite as often. Okay, so you've at some point you've built a hotel the size of a large cruise ship, maybe a couple of cruise ships lashed together, and you rotate. And so to turn that into a settlement, there's only a couple things you have to do. You have to rotate faster in order to get 1G, and then you probably have more robust life support system. That you're probably able to produce your own food, which is not necessarily something you'll have to do on a hotel. Now, that's great, okay, except that if I've done nothing to simplify the construction of the second, third, and fourth, and fifth settlement, then I haven't really done my job, because remember the job changed a little bit. So I think what you want to do is you want to do something similar to John Menken's hypermodular space solar power system. Basically, he's talking about building space solar power systems out of maybe 20 discrete components and building literally thousands of each of those components. And the reason this really buys you a lot, several things. One is that you get good at building them. You can use mass production techniques. If you're only building 10 of each module, well, then the automating it's crazy, But if you're building 2,000 of the same thing and you're going to put it together, that's it. Now the second thing is that if you standardize the interconnections and so forth and so on, you can teach robots to say, you put these two parts together, you're going to have to do this thousands of times. And robots are really good at that sort of thing. They're not so good at doing one-offs. They tend to be very expensive for that. So while you're building these hotels, you want to be modularizing the system. As you learn how to do it better and better, you want to launch more and more parts. And you want a standardized cargo system. What you'd really like to do is take the big boxes that they ship around on trucks and trains and so forth and so on, and just take that exact same system and just stick it in the launch vehicle and fire that sucker up. So you're completely integrated on a mechanical level with the ground transport, because that's how ground transport is done today. It's all with these modular, basically rectangular brick things that they push around. And so we need to integrate that right into our system, because you're going to be building a whole lot of stuff on the ground and you're going to be shipping it up into space, and you need to automate it as much as you can. When I did the calculations that said $5 million would allow you and your spouse to move onto a space settlement, call up on a 2 space settlement, that assumed that the purchase of materials and construction costs would be about equal to launch cost, which is a major assumption, because that's not the case. Communication satellites today, for example, generally cost more than the launch, quite a bit more than the launch. But if you're going to do that, you need to have you have to have it be standardized if it's going to work. So the things we want to work on while developing all this stuff is standardization of interfaces, standardization of things, repeated construction of the exact same thing over and over and over and over again, because otherwise you're never going to get the price down below the cost of transportation. If you assume the transportation costs are among those with the most optimistic visions of the Falcon Super Heavy that we can have. So that's a sort of a picture, of how one might go about building the first N settlements, where N is a largest number, 10 or 15 or 20 or something like that. You build a series of hotels. Each hotel gets bigger and better and also becomes more and more standardized, more and more modular parts that are used over and over again. By the time you start building your space settlements, you've modularized most of it. You know how the interfaces work. You just have to repeat what you did, make the hull stronger, and deal with a few other sort of major things like a space farm. Thank you.
I'd like to comment on the example he gives is really reinforcing the idea that what you're doing and how you're wanting to do it really drives everything. Now, it's not clear to me that standard freight containers would be the way to go. Freight containers were designed for this intermodal application. Cars are shipped mostly in a different way, and that's standardized, and it's more appropriate for most cars. But I think that standardization, however it's done, we need the new standardization guru of the sort that created the intermodal system. I think weight and the ability to recycle the container in orbit is going to be essential, because a structure that's heavier but can be reused is probably a better one than the aerospace approach of, very, very low mass but expensive.
It's not just the container, it's also all the stuff you put inside to brace everything. Right, there's a lot of packing material. You go get your box from Amazon, it's got like 3 boxes and 4 things of this and 7 of those and 8 or 9 of those. That stuff you want to be able to use in your system too.
And then also we have to say with the Starlink satellites, I don't know exactly how the structural path worked for stacking those satellites, but I very much doubt that the bottom satellite handled the axial loads of the whole 60. So there's creativity, it's what you have, what you need, and your creativity that drive construction. And I think that the example of using permafrost for a dam, which Farley Mowat wrote about in the 60s in a book called The Siberians. The chapter on Chernyshevsky talks about that. You need that kind of creativity. Do you have any comments or questions?
Well, in talking about sourcing materials for in-space construction, the path we're taking is, again, kind of incremental. Initially, we'll launch raw materials from here on Earth and then use robotic systems to process them, to make structures or other elements and assemble them together. But we want to evolve to an approach where we can use in situ resources to do that construction. So we are taking some initial steps towards that. Right now we have an experiment on the space station called the Refabricator. The Refabricator is a kind of mini fridge-sized payload that combines a plastic recycling system with a 3D printer, and basically it's doing very much what we were just talking about. It's working towards the capability of using waste materials on the space station, such as launch packaging materials. Right now, on a typical cargo launch to the station, there's roughly 25 pounds of Ziploc bags and bubble wrap and foam used to protect stuff going up to the station. And that packaging material just becomes trash that the astronauts have to shove into a corner somewhere. We're working on a capability to recycle that into feedstock for in-space manufacturing. And then another project we're working on is funded by DARPA, is looking at repurposing launch structures such as the ESPA ring. The ESPA ring is a big aluminum ring that goes in between a rocket and the large satellite that the rocket is launching. And it typically carries a number of secondary payload small sats on it. But that ring, after it releases the small sats, becomes trash or space debris that has to be disposed of. We're working on a payload that is designed to actually chew up most of that ring and melt the aluminum down and refashion it into segments for a big antenna reflector. It's a very challenging project with a lot of technical risk, a lot of new technologies we need to develop. But one of the main reasons we're pursuing it is that if we can show that it's possible to take a piece of space debris and transform it into something of value, then my hope is we can do an end around the whole space debris problem, which currently is kind of intractable because nobody wants to have to pay to clean up the space debris environment. But if we can turn space debris into something of value, then hopefully we can create a commercial venture that would just go up and clean up the space debris environment and actually make a profit at doing it. And then, hopefully longer term, those systems will be able to ingest materials that we can get on the moon and on asteroids so that we can really get to in situ resource utilization and be able to afford to make the big structures we need to support human settlement.
About 2013, I did a look at how much mass had been delivered to the space station and then deorbited, not for recovery like the Soyuz capsule, but burned up. And I believe that by now that total mass exceeds the 900,000 pounds of the space station itself. So the payoff for recycling is substantial. Now, you can't necessarily build a second ISS, but there's a lot of stuff that you can do, and we need to learn how to do that, okay? Some of my earliest work was on recycling, space work in the early 80s, was on how to recycle the shuttle external tank. People came up with ideas for making tanks into space stations, et cetera, but the planned use of the shuttle was going to exceed any plausible use of external tanks for actual habitation use. And so I said, well, if you can't do anything else, can you chew it up and recycle it into propellant or large space structures? And I found that there are techniques for making aluminum alloys, vapor deposition and molten spray deposition, that get better properties than ingot metallurgy. Okay, there's a process called the Osprey process, which is used, I don't know if it's still used, but it was used back then in BMW piston liners. So there are a lot of things you can do. The 2,000 plus tons of orbital debris in LEO, about 35 to 40% of that is Russian rocket bodies, okay? And in 2010, a colleague of mine presented some slides of mine at a meeting in Moscow, and it was about orbital debris. An economist from the Russian Foreign Ministry, Valentin Nataluha, buttonholed my Italian colleague and said, the Russian position on this is not to deorbit orbital debris, but to recycle it in orbit. Now, I think what he was actually saying is, you want to buy our garbage for a good price and take the responsibility for any later debris creation? But this is an opportunity. There's a lot of stuff out there, okay? I'd like to invite the audience to answer any questions or make comments on anything that we've said so far. Okay.
Al, you had talked about wanting to be able to build small modular pieces and then be able to grow over time. I'm envisioning these large structures that would have an inner volume to them where people would be living inside those, unlike a hotel, which could be very well some of the competing ISS type competitors that have different modules. But I'm having a hard time imagining how I go from small modules that very well could be like you're describing for a space hotel and make the big leap to some very large surface area on the inner volume that I can live in. Can you help me connect those dots?
I mean, there's a discontinuity there, right? When you cross over the threshold that you can't launch with inside a fairing, a whole bunch of stuff happens. Now, I would recommend doing that and making it just a little bit bigger than the fairing needs, because it's a little easier to do. But yeah, it's a discontinuity. I mean, all will not be smooth.
There are a couple other steps. One is inflatables. Okay, so a Bigelow module can be larger substantially than the diameter of the fairing used to launch it. Okay. The other is that if you make a large mylar balloon or Kapton balloon and inflate it, have it be some metal on both sides so that when you can stretch it and then relieve the pressure, it still stays the same size. Then you can start doing vapor deposition, and when it gets thick enough that you can start doing molten spray deposition. If you were to take all of the spent stages in low Earth orbit and recycle them into one large structure that could handle 1 atmosphere, it would be about the size of the Air and Space Museum in Washington, D.C. Okay. That's doing stuff with the material that's already in low Earth orbit. And that's leaving out the 800 tons of spent stage debris in GTO orbit. Okay.
I think you.
Okay, yes.
Bob, one of the points you noted with the trusselator, in the past, when looking at spider fab and so on, you've noted it could build very large trusses. What sort of time frame would we be looking at for the large trusses of kilometers across and so on that would be useful in space settlements?
Well, that all folds in with, funding profiles and how long it takes to get an experiment actually flown. Right now, we're taking baby steps. The experiment we're working on now, which is slated to fly in 2021, will basically be manufacturing 2x4s on orbit. So still a ways away from making kilometer scale systems. But the next step then is to fly a system that can make a 50 or 100 meter long truss. We could always do that 3 years from when the funding starts. Yeah, I'll put it that way. And then, once you can do that, it's building the kilometer scale systems will still take further work, in main part because you're going to have to get those systems to be very reliable. Making a kilometer of stuff, your system is going to need to do many, many operations over and over again without failure, or being able to adjust for and correct for failure, and implementing those capabilities. I would say that would be on kind of the 10-year time frame.
Okay. So we are talking about one generation that's already in the works, and then you're talking about, it seems to be about 3 generations beyond that first generation?
Two or three.
2 or 3. Okay. Very good. For your competitor, given that something like that would be about 3 generations out from 2021, 3 generations of hardware, however many years that is, vapor deposition and/or the process, the Osprey process that you mentioned, would be able to build on such a structure, I would assume. Is that correct? The combination of those two together? Am I looking at that?
One is a truss structure, another is a tank-like structure,
Yes.
and, you may connect them in various useful ways, but they're distinct things made in distinct ways, probably for distinct
But
purposes.
the key is that are we looking at things that could arrive at the same time, is what I'm saying.
Oh, yeah. I don't know how long it would take to get a space-qualified test of vapor deposition or molten spray. I mean, molten spray deposition really can be done at the droplet level, which is additive manufacturing.
Mm-hmm.
But I don't know, okay? Any grad students interested in metallurgy? These would be great topics that have a space payoff.
Thank you.
Okay, well, first of all, kudos to all three of you for starting to talk about recycling of plastics and foam and trash that goes up. You know, in the height of the shuttle program, they were even putting lead ballast in the back of the payload bay to fix center of gravity problems. I mean, you talk about dead weight. That was it, lead ballast. Okay, at some point, we moved from recycling to cannibalization. Al, you talk about making bigger structures. That's not necessarily recycling. You are cannibalizing the old structure to make a new, much bigger structure. Okay, then my real question though, this is gonna sound snarky, and I don't mean it to sound this way. I'm asking a dead serious question. I read The High Frontier in 1977. I've been a huge proponent of ISRU ever since. But unless I'm mistaken, nobody has ever made even something as simple as a crowbar from extraterrestrial materials, from non-terrestrial materials. So I'd like to ask all three of you, this idea has been around for a long time. This is now 2019. Give me your estimate of the year in which we will manufacture our first tool, and it can be as simple as a crowbar or a shovel. I'm not trying to be high tech. So give me your estimate of the year.
I
Decades.
think it's already been done. I think Planetary Resources got some asteroid material and remanufactured it. Chris, can you?
We did, yeah. It wasn't in space, and we didn't go get it. It came to us.
Well, what about some material you find out there?
Iron, nickel, and cobalt readily available.
Well, I know everything's readily available. I'm talking about what's your estimate for the year in which we as human beings manufacture our first tool from non-terrestrial materials that we get up there. And again, I'm not trying to sound snarky. I'm really not.
Yeah. Let me shift it to give you a different perspective on the problem. If you're living on Mars, you know, forget about next day delivery. You can only get next year delivery every other year.
And that's the reason I'm asking the question.
Yeah. The people that will actually be working and living in space will be the recycling experts. You know, there is an optimism about almost infinite resources in space, so we don't have to recycle. No, the people in space, the most important resource they will have is their own midden, their own junk pile. It'll be easier and more reliable and cheaper and safer and quicker to recycle, to mine the midden, than to get stuff from any other body in the solar system.
I agree with everything you've said, everything. So let me try to make it simpler for you. Do you think we're talking about years? Are we talking about decades? Or are we talking about generations?
Talking about decades.
I think it's years. I think very soon after we get a semi-permanent presence back on the moon. You know, I know that NASA's in-space manufacturing program and several, you know, Skunk Works, the Swamp Works, they're actively working on using regolith and other materials we can get there to make landing pads and other such things. So
all right.
And radiation protection. I mean, pile stuff on top.
and you gotta have a reason to go there. So
Well, and that's the other reason that if we're really seriously talking about a serious reboot of the ONeill Vision, you know, ONeill Colonies 2.0, this discussion needs to be central in that reboot. And that's both on a technical level and on a political level. Because I'll tell you, I was at NASA for 22 years, and NASA's not interested in ISRU. They're not. And the reason is that NASA doesn't do visions.
The White House just released a policy, the top 5 R&D initiatives for the next several years. ISRU made it into the top 5.
But all NASA priorities last until the next NASA administrator.
And so, well, look, I mean, I'm not trying to start a debate. I'm just saying it's an important issue, and it needs to be central in our discussion of a reboot of the ONeill Vision, because a lot of it has been dropped, and I think we can all agree it's central to the concept. Central.
Manufacturer is not making that flight available, right? You've got a QC function, you've got a material testing function. So manufacturing it doesn't mean that it's flight ready.
Yeah, I know. I know all about that because NASA was going to charge me. Well, he's talking about the issue of making something flight ready, flight certified, how expensive that is. Yeah, some of you are probably EMTs. You know, the little plastic thing you put in the mouth when somebody isn't breathing so you can put the mask and the ball and breathe for them. You know how much the engineers at JSC wanted to charge us to flight qualify that piece of plastic? No power, no data, no nothing. A piece of plastic. $125,000 is what they wanted. So that system needs to be fixed.
We flew it with the Russians for 10 grand.
Okay, who's next?
Actually, this is kind of a segue almost. So I was looking at or listening to all of you, and a question that came to mind was, well, we're clearly thinking about building in space. Currently, it's obviously cheaper to do all the manufacturing on Earth and then send up the refined materials up to space. However, there will be a tipping point, and according to your opinions, at least, what is that tipping point? What are we looking for in which it becomes more feasible or economical to make our parts in space rather than launching them?
Yeah, it may depend on things like when the LSST, Large Synoptic Space Telescope, or Survey Telescope, starts looking at finding 50 or 100 times more small near-Earth asteroids and near-Earth objects. That may become a tempting target to go, because we've seen most of the kilometer asteroids. We've seen some 100-meter, a few 10-meter. We're going to find a lot more, and some of them are going to be closer, more accessible. And that could become a target of opportunity in 5 years. I don't know.
What would you be looking for, though?
I think it'll be obvious. I don't think you're going to have to, pour through ancient documents and read the last page of the New York Times. To me, it was pretty obvious when Planetary Resources and DSI got started up that they would not, that there wasn't a customer at prices that made sense. And I think it'll be fairly obvious, if we're not deluding ourselves by how much we want ISRU to work, as opposed to you can just sort of look at it and go, well, we're not even close.
And maybe just a more fundamental principle is when the manufacturing cost plus the transport cost to any point in space is less than the corresponding manufacturing transport cost for that same point in space from Earth.
So you'd be looking at something like economic value, so monetary value, or monetary and chronological cost?
Money wins out.
Okay, Kim?
I'm partly taking advantage of the fact that Rob's on the stage. I read through, a couple of years ago now, the Wikipedia article on the Van Allen belt. And if you get down far enough, there's a section that says how to disperse the Van Allen belt. And it harks back to work you did with Robert Forward. And is that truly a viable thing? It never gets discussed. I don't know how much of an issue it would be if there was a lot of infrastructure in space, but you moved away from it, and I just wondered if you could talk about it a bit.
Sure. The concept we were working on was looking at whether it was feasible to deploy long conducting tethers in space and charge them to very high voltages relative to the space environment so that their electric field would deflect the charged particles as when they pass near the tethers. The radiation belts form because the dipole field.
It's a natural tokamak.
It traps the particles and they kind of bounce back and forth between the poles. But if you deflect them so that the particles are going more along the magnetic field lines, they can penetrate down, further down into the upper atmosphere, and they'll dissipate their energy in the upper atmosphere. The Air Force is looking at a different way of doing that using transmission of very low frequency waves to try and scatter the charged particles into what are called the loss cones. We were looking at deploying a system of 12 or maybe 20 100-kilometer long charged tethers on orbit, and the analyses we did indicated that it was technically feasible. There were definitely some very significant technical challenges. The main one being how do you charge up a wire in space to really 100 kilovolt level voltages without the whole thing just arcing or melting. A lot of technical challenges to be addressed there, but assuming you could figure that out, that system is technically feasible. But question came down to who's going to pay for it. It's another. It's like the space debris problem. You got the space radiation problem. Who's going to pay to actually do that? And until somebody some rogue nation or something lights off a nuke in space and creates a very bad trapped radiation belt, it's unlikely anyone's going to step up to pay to have that done.
Yeah, let me comment. The radiation gets worse as you get higher, up to 3,000 kilometers or so, half an Earth radii high, and that is kind of where it's worst. Now, the South Atlantic anomaly is there because the Earth's magnetic field is offset, and the radiation spirals around the field, and so it gets closer to the Earth over the South Atlantic anomaly. Okay, so you're just seeing the same radiation you see elsewhere, but at a lower altitude. Now, what that says is that it's the atmosphere at that altitude that cleans up the radiation. If you put large amounts of mass that are comparable to the mass at that altitude over that region, you can actually start to soak up the radiation belt, okay? Now, for example, a 10,000-ton solar power satellite climbing from LEO to GEO would probably provide a rain shadow that it would absorb a lot. The dose that they would experience would be much less than for a much smaller thing, okay? But it requires large investments. But you're a collection of things in equatorial orbit, even though it clips the edge of the Van Allen belt, would contribute to that, to soaking up the belt, I think.
Yeah, a little bit, but probably not a lot.
One thing to keep in mind is the radiation belts are continually being fed by energetic particles coming in from the solar storm, and they kind of get dumped. They'll get dumped in by a solar storm. You get a whole bunch of particles, but they're always migrating in towards the upper atmosphere. So there's a continual sink that's sucking particles out of the radiation belts. So you get more particles dumped in, and they kind of propagate in, and then they dissipate out.
When we did
so
the starfish,
flow. So if you want to clean it up, you need to sweep them out and then keep sweeping them out.
yeah, the starfish high altitude experiment over Johnston Island, I think around 1962, created a intense enhancement of the radiation belt, and it went down over a period of months.
So if that was done, at some point, I mean, obviously, we're not making plans here, but that would create the same ELEO environment that would allow a significantly lower radiation for a settlement in any orbit?
Just more so, you know, you can go further, and it's not a matter of zero, it's a matter of decreasing the dose.
Thank you.
That's a lot of pressure. First, a small story that when Henry Ford first got started, he used to specifically order his truck parts for his cars and his trucks in specific size boxes of specific size wood. They would be delivered to them, and then he would take the wood and use them to make truck bodies. So, you know, when you're talking about recycling, it's also partly, if you think about how that you're going to use it later, what you use and how you pack it makes a difference. And sometimes it's just, forgive me, it seems that the folks at NASA, their focus is not on can we reuse this, so they look for what is the most efficient way to do what they need to do. So when it comes down to that point when we're doing commercial as opposed to NASA launches, that I think that kind of orientation is going to change. My question is, of course, completely different. I know that I've often heard people talking about, you know, cleaning up the space debris and so forth, but has anybody done any real research on what it would entail? Because my understanding is that, you know, it's really dispersed. There's it's really
the first challenge is collecting it because it's in a wide range of orbits, but there are some tricks available.
Right, but has anybody ever actually done any analysis of what that really would entail? I mean, you know, it's there, it could be used, but it's sort of like, you know, drops of water across a field to get water. If you're really thirsty, you do it, but it'd be really energy intensive. At least that's my understanding.
Yeah, well, one of the things is the single greatest collection of launches is to the International Space Station. Generally, the vehicles that launch to the station leave a spent stage in lower orbit, but it could be brought to the station, okay? And that would be adding like 1/3 or 1/4 as much as is flowing to the station, and that could be recycled. I believe it was about a year ago that Elon decided he was going to give up on trying to recycle the second stage. And I thought that made sense. I was surprised it took him as long as he did. Or to reuse the second stage. It costs more, the heat shield, and the benefits are less and all this stuff. But there's a point at which he will start thinking about, can we reuse this in orbit? Okay, and he may have already started thinking about that.
As you noted, one of the main challenges in cleaning up the debris population is that the objects are in wide range of altitudes and inclinations, and it's very expensive in terms of propellant use to get from one inclination to another. However, there are some techniques for propelling things around in space without having to burn up propellant, such as electrodynamic tethers. So that is one of the reasons that we and Joe and other folks have been trying to fly electrodynamic tethers and prove out that capability, because if you've got that capability, you can, you know, take your time and kind of sail around the orbital environment and pick up debris and collect it and bring it to a central recycling or repurposing area.
I should mention that the Naval Research Lab has an experiment called Tipsy, Tether Electrodynamic Propulsion CubeSat experiment, that I came up with the basic concept for and wound the tether, specified and wound the tether. And it's in orbit now, and sometime between now and probably the end of October, it will be deployed. It'll be a 1 kilometer tether. It will not have enough power to climb to counteract its own drag. It'll just re-enter within a month or two. but it will test some crucial things for electrodynamic propulsion. And it should be visible through binoculars or telescopes as a long line in space, not as bright as SEDS 2, for those of you who saw SEDS 2 in 1994, but it will be almost as bright. And there should be some TV images of the deployment. Will take only about 4 minutes. And we're trying to figure out the best time and place to get good imagery. And that's discussions going on this week. It was launched back in June 25th, as part of the STP-2 experiment on a Falcon Heavy, one of 25 payloads launched. And Rob has 2 payloads on that same mission.
All right, thank you very much.